So today, with day 4 of our probability adventure we're going to be taking a peek more today at conditional probability. Now, we've talked a little bit about this before, where one event determines what's going to happen with some of the others. So for instance here, given events A and B, so it may even be an event C, D, whatever, but multiple events. Conditional probability is the probability of an event B occurring knowing that A has already occurred. Now, for instance, yesterday we had an example of if I have marbles in a bag and I draw a marble out, but I don't put it back in, how does that affect my probability of the next marble I want to draw? That would be an example of this. So the notation for something like this looks like this. It kind of looks like the probability of B divided by A, but that's not what it means. The way I would read that would be the probability of B given A. In other words, here's the probability of this event happening given this event already happened. My probability of drawing a purple marble given that I drew a yellow one my first draw, or something like that. So when I'm trying to actually calculate this, and it won't just say BA, normally we'll come up with some actual words to put in there. But if I'm looking for that probability, I take the probability of A and B occurring, and we typically are going to divide by the probability of A. But there are some ways we can even simplify that a little bit, and we'll touch on those as we start to do some of these. Because sometimes it can be trickier to deal with a formula than it is to just use a little common sense and think about it for a second. So again, this is one of those, just stay with. We're going to see plenty of examples that'll make this a little bit more sensible. So, okay. Example 1. Mitchell drew a card from a standard deck of playing cards. What's the probability that he drew a queen given that the card was red? Now, here's the part that I have to think about a little bit. Okay, we'll use the formula this first time, and then we'll think about it a little to see if we can simplify it some. So my probability of A, okay, so what's the probability that he drew a queen given, okay, the given part is my A, that the card was red. So if I was thinking about a card being red, that'd be 26 out of 52. Because remember again, hearts are red, 13 of them. Diamonds are red, 13 of them. Okay? The and just means I'd multiply that by the probability of getting a queen. Okay? Queens. There's 4 of those in the deck. So I'd multiply those together, and then I would divide by my probability of A, my probability of the card being red, which is 26 out of 52. Now, there's a couple of ways I can try to tackle this. Some of you just looking at all these fractions are about ready to, crumple up your paper and throw it somewhere. There are some ways to simplify this, but here's what we'll do for right now. And I'm going to do some work on the side, too, in case you don't want to deal with all of this craziness. So if I want to go to the calculator because I feel more comfortable with that, okay, I can do it where I multiply with my fractions, and then I'm going to divide by 26 divided by 52. And of course, we always go back and do math, enter, and I could get it that way. That's one option I have. Well, what if I'm somewhere where I don't have one of these calculators, or my calculator doesn't do the fraction reducing, or okay? Here's my other way I can look at it. When we're doing these, so I've got 26 over 52 times 4 over 52. When we divide by a fraction, okay, when I divide by 26 over 52, Remember, when we divide by a fraction, that's the same as multiplying by its inverse. And watch how quick I'm going to make this simplify without even using a calculator. When I flip this, we've said before, if you see the same values in different places, you can cancel them. You can cross-cancel. You can cancel top to bottom. So I can cancel 52s, and it wouldn't matter. I could have done these two if I wanted to as well. Cancel those, and what I'm left with is 4 over 52. And if you reduce 4 over 52, now I get the 1 out of 13. So that's mathematically, formula-wise, how I can do it. And we're going to talk in just a second about how I can do it without the formula. Yes, sir?
Isn't there only 2 red queens, though?
Yes. Okay, good question. And that actually is what I was about to lead into, where we might not need the formula. Because if some of you think about it, because some of you, I like the way you're thinking. Some of you are saying, well, wait a minute, there's 2 red queens. Why am I using this for? Because when I'm using the formula, I would use all of the queens and then all of the red, and I would simplify it at the end to find it. But let's do it your way and see if that works the same way. So let's consider, because you guys are sitting there going, okay, so Harty, there are, let me get the calculator out of the way. There's 2 red queens. How many red cards total are there? What's 2 over 26 reduced to? Okay, so you can on these, if you stop for a moment and think about it, you can simplify this where you don't necessarily have to use the formula. But if you need to or you can't figure it out, it's something you can fall back on. So on several of these questions, I'm going to use both. But then after a while, I'm going to start saying, okay, can we just use this using common sense? And we'll talk about that. But I'm glad you mentioned that, because that was a really good common sense way of thinking about it. And you got to the right answer.
Simplify the fraction should give you the answer.
So, okay, let's see how this next one works. Let's play with it both ways here for one more. So a number from 1 to 100, oh dear, is randomly selected. What's the probability that it's a perfect, oh my, spell check, Harty, square, given that it's an odd number? Okay, so given that a number between 1 and 100 is an odd number, first thing, how many numbers are there from 1 to 100? 100. How many of those 100 numbers are odd? 50. So 50 out of 100. How many perfect squares are there on my way to 100? Let's think about this for a minute. 1. You're like, oh my gosh, all that stuff him telling me before that I need to know my perfect squares up to 10. I didn't know I'd actually have to need that for probability. So there's my perfect squares up from 1 to 100. So there's 10 of them. So again, if I'm sticking straight to the formula, that's my probability of A and B. Multiply those together. Divide by the probability of A. And I think you're going to start noticing a pattern develop here. You're like, wait a minute. Could I do what?
Are you looking for an odd number perfect square?
That is basically, well, what's the probability? We'll talk about, yeah, we're basically looking for an odd perfect square. Sure.
You know how, like, you have you're multiplying it and then you're dividing it?
Uh-huh.
Are you always dividing it by the first set?
Uh-huh. Yeah, some of you are catching on to what we're kind of thinking here, because you're like, well, wait, if that's true, because last time those just canceled out. So then these are just going to cancel out. So it's 10 over 100. And if I reduce that, it's 1 out of 10. Because if you stop to think about it, you're like, well, wait a minute. Let's see if we can do it that same way that we did number 1, where we just use some common sense. So you're like, okay, perfect square given that it's an odd number. Okay, so out of my perfect squares, how many of them are odd numbers? 1, 2, 3, 4, 5. How many odd numbers did we say there were? Well, let's see. Hang on. Odd, perfect squares. How many odd numbers were there? 50, right? 50 odd numbers. 5 over 50 reduced is 1/10. Okay? So there's a whole lot more common sense to this that we may choose to want to look at. So if you can do it using common sense, as long as you think about it, maybe write it out this way, that's a fine way to go about it when you're doing the conditional probability. You don't have to make this complex. So I like the thought process we're using with this. We're on it today. So of course, then now that we're on it, I have to throw a twist in. So we have 62 people that are taking a yoga class. 48 people are taking a spinning class at the gym. I have no idea what that is. 15 people that take yoga also take spinning. If a person from these groups is selected at random, find the probability that he or she takes yoga if you know they take spinning. Okay, there's a whole bunch of stuff going on here. I like kind of getting a visual on this one. So let's do this. Have any of you played with Venn diagrams before? You're like, okay, what's that again? All the time. Okay. So a Venn diagram basically is when you have information that overlaps. It kind of gives you a visual of how this works. So I've got 15 people that do both. So we kind of work our way backwards. Okay, thank you. So what we're going to do here is the people we have in common that take both go in the middle, wherever the overlap happens to be. So once I have that, here's the part that gets, this is the one part that's tricky with this. So here's what they do together. So we're going to have some yoga. We're going to have some spinning. Okay. Now you want to write down, there are 62 people that take yoga class. You want to put 62 here, but that'd be bad. Why would that be bad? Because I already have 15 people that are accounted for that are taking both. So if I have 15 people that are taking both and 62 total are taking yoga, how many more people do I have to put here? 47 just taking yoga, 15 taking yoga and spinning gives me 62 yoga people. So then how many just spinning people do I have? 33. Now we're getting somewhere. Okay, so now let's read into this and see if we can make this go easier than trying to do this big old fancy formula. Find the probability that this person is taking yoga if you know they take spinning. If you know they take spinning and they take yoga, okay, so basically this is a question of yoga plus spinning over spinning. Okay? Yoga plus spinning, 15. Spinning, the whole circle for spinning here, which is 48. So you start to see, I really don't have to do the big fancy formula multiplying everything out, but I do have to get an idea of how these values work, and sometimes a picture can help me. That's a good point, thank you. They are both divisible by 3. Yep, need to reduce, always need to reduce when we can. I got so pleased that we were going along with that, I forgot to reduce. Details, details, details. All right, so let's do one more like that. You're like, oh dear. Until I'm feeling that we're comfy. We'll see how comfy, how long it takes to feel comfy. Maybe it'll go quicker than I'm thinking. So, of the 30 students in Mrs. Smith's math class, 13 are athletes and 9 are in the band. 3 of the students are also in band. Oh boy. Let's see here. Oh, that's what I misworded. 3 of the student athletes are in both, excuse me. I'm sitting here, I'm looking at that. I'm like, wait a minute. Okay, so no. 3 of them are in both. That's not even close to what I meant. Okay. So we've got athletes, we got band members, and then we got this 3 that do both. So, how many just athletes do we have?
13, 10.
Okay.
And 6.
Okay. So let's see here. If one student is chosen at random, find the probability that the student is in band if it's known they are not an athlete. Okay, so band, no athlete, over no athlete. So band with not this crew that are athletes too. So 6. Ooh, now this is going to get interesting.
6 over 8.
No. How many students in the class are not athletes?
Oh,
How many students total are in the class?
Wait,
30.
30 minutes.
30. How many are athletes?
10,
no.
20.
30.
What?
13.
So how many aren't?
7.
Ooh. Okay, so the Venn diagram helped me figure out where that combo is. But notice, this is only 19 people. It didn't include everybody. I got to read carefully. Ooh, that was kind of tricky in a couple of ways here. But again, that's why having the picture can help. Okay, sometimes, and this is the type of question, again, that'll come up when we're looking at your post-test here soon. Okay, these tables show up on there. So in our example, this table shows the results of a poll of 50 randomly selected students, because if I add up all these numbers, I get to 50, who are asked whether they prefer to watch hockey or football. Find each probability. Okay, so this first one says prefer football given that it's a girl. Okay, so basically what this is saying is how many girls like football over the number of girls. 6 over 22. Okay. So basically when you're making your numerator, it's the two things together over the second thing. Girls who like football over girls. Okay? Just like in the second one, it's guys who like hockey over the number of guys, or over the number of boys. So what's that fraction going to look like? 10 over 26. 5 over 13. So again, I have to pay attention to everything as a whole. Yeah, the book. Wait.
Oh, wait, never mind.
Did I? Oh my gosh, Harty. It's always fun when the math teacher's having issues adding in the morning. Thank you. Yeah. Oh, hang on a minute. What did I do? What? Okay, let's go back and look at this. Girls who play football. And the second part was the girls. The girls went on the bottom. Let's reread this one again. I made an assumption. That was bad. Boys who play hockey. What should have been on the bottom? Hockey. So the 10 is still right. But how many people like hockey? I'm going this way. 26. So my math was right before. My labeling was just awful.
What does the bottom say?
Hockey. Hockey and Harty scribble. Yeah, mathematically we were right, just didn't have the labeling down right. Because in my mind, I flipped those two things around instead of looking at what was second. That has to be what goes in the denominator. So good catches on many fronts there to make sure that's going well. And again, it kind of shows in these videos the humanity of even the math teacher. Okay. see if we can get this straight here. If we get comfortably through 5, we might go down to the frequencies at the bottom and then just be done. Okay. Table shows the results of 150 randomly selected middle school students who were asked if they take French or Spanish. Okay. Notice straight up probability on the first one. Probability of a 7th grader taking French.
Tells you right there.
It tells you right there. 25 out of the 150 students. Okay. And you're like, well, how do I know there's not a second part? Because there's not that slash there that like there is maybe in letter B here. Okay, that's when I have to start thinking. So like when I get to letter B, I need an 8th grader given that they're taking Spanish.
So would it be just both of them added up?
So 8th grader Spanish over everybody that takes Spanish. So 8th grader taking Spanish is 33. How many total Spanish students are there? 68. And that doesn't reduce. So again, if you need to see it verbally, kind of write it out quick like I am here, it does make it a little bit easier to deal with. It's a heck of a lot better than dealing with all those crazy fractions. Okay, takes French, but a 6th grader. So 6th grade French over 6th grade. So 6th grade French. 6th graders, I'm just adding them together. So you kind of see where I'm heading here. Now, instead of doing D, I'm going to jump down to number 6 because I see something that we haven't dealt with yet. I'm just going to look at A, B here quick, just to make sure we're on top of things. So 6A, a junior that did not attend prom. Out of everyone. How many people do we have here? Grand total of people. Everybody. 200. So 56 out of 200. And reduce that. Now letter B was the one I specifically was staring at going, let's see if this gets anybody. Maybe, maybe not. Okay, probability did not attend prom given they're a senior. So that would be senior no over senior.
So 19 over 97.
Because I got to get all those seniors in there, and that one doesn't reduce anymore. Okay, I'm feeling comfortable now that we kind of got a grip on this. So again, you see that slash. Sometimes you may see that as a comma instead of the slash, but the meaning behind it's going to be the same with that. So then the last thing with the tables that we can play with are what are called frequencies. So basically what we're going to do here is we're still going to use the tables the same way, but we're just going to do a little bit of math to get there first. So table below shows the number of first class and coach class passengers on a plane who checked 1 bag, 2 bags, or no bags. Find the joint relative and marginal relative frequencies and then find the probabilities. So we got to do a little math first. How many total people were flying? That's our first job. $160. Okay, so 160 total. So once I get that 160 total, now to start getting the values over here, I have to take each of these, okay, and I'm going to divide them by 160. So for instance, because what you're doing is we're calculating, we're making a table that comes up with every possible percentage of people that would do it. So like for instance here on this first one, I'd do 16 divided by 160. Okay? And we're just going to the decimals, no fractions here. Because what you're going to see at the end here, once we get this table made, is that all the decimals are going to add up to 1. And they better, because if they don't, we've lost somebody somewhere. And that would not be good to lose people. Bless you. And then we're just going to go ahead, and as we get to the bottom on each of these, we're just going to add the columns up to get the values. So you see what I'm up to. I'm just taking whatever numbers in the box to begin with, dividing by the total each time, and then just writing the random decimals. Well, they're not random, but in here. So I'm actually going to help out here and fill in the rest of these for you. And when you get to that last column of total, we're just adding horizontally. And if things have been done correctly, both these two and these three should add up to 1, which means we covered 100% of the people that were on this particular flight. So that actually is the most work of this whole thing. Because now it works just the same way that I was doing it before. Probability of a coach class passenger that did not check any bags. Coach class, 0 bags. 0.1125. And again, you can leave it as a decimal. You could move the decimal point 2 places. Call it a percentage. Okay, they're equal to each other, so I'll be honest, I don't care which way you write it. Probably it means most of you are going to go decimally, which is fine. Not a problem. But there's, of course, going to be a little bit of thinking to this. A first-class passenger that checked at least 1 bag, which would include 1 bag and 2 bags, because it says at least. It doesn't say just 1. So 0.1 plus 0.075 gets me 0.175. Okay, again, if you want to turn it into the percentage, move it 2 decimal places to the right. It's 17.5. Either one's fine. Okay, now we get to kind of put it all together. Probability of flying coach class given they checked 1 bag. So coach 1 bag, the combo, divided by checked 1 bag. So I'm like, okay, coach 1 bag. And then the 1 bag total. Okay, not just coach. And I get my answer. So it just means I got to take it 1 step further when I do this. And then the final one, check 2 bags given first class. So first class, 2 bag over first class. So first class, 2 bag over first class. And get my decimal. So as you can see, it's not that these are terrible that we're moving forward, you know, with our step forward on our probabilities. It's just a little more thinking that you've got to do. So the key is out and about for this. Tomorrow we're going to do a review basically of all of this stuff. We're just going to throw it all together. And then next week we can wrap this up a little bit with samples and surveys and be ready to finish up the year's activities.